I'm Anil Kumar. Welcome to my session on exam review. We'll now discuss limits. I hope this session will help you recollect all what you've learned about the concepts and how to apply different techniques to find limits of functions. We'll touch upon these topics: limits of continuous functions, limits from graph, why limits may not exist, limits at infinity, trigonometric functions, limit, one-side limits, limits of piecewise functions, and then we'll take up examples pertaining to limits of indeterminate quotients. Techniques which you have learned are factoring, substitution, rationalization, L'Hopital's rule, and squeeze theorem. I'll mainly discuss topics which you might have forgotten or not laid much emphasis on. So to begin with, let's talk about the definition itself. We say limit as x approaches a for any function f of x is equal to L. Now when we say this statement, what do we mean? That's very important to understand. So we actually mean here that the value of f of x is arbitrarily close to L. So here we mean that value of f of x is arbitrarily close to L, right? This is what we mean. So when we say it's equal to L, it is not really L. It's very, very close to L. It could be as close as we desire, but it cannot be L. It may not be L, I should say that. Okay. By taking what we do here, by taking x sufficiently close to a, right? That's what it means. So I hope the statement is clear. So we are going arbitrarily close to L as x is sufficiently close to a. That is the basic concept of limit which we have learned. Correct? Now let's see how to find limits of functions when they are continuous. Now when we say continuous functions, it basically means that the graph of the function is continuous in its domain, right? So it could be anything kind of like this, right? Whatever. So we are talking about any continuous function, right? So if for a function, if you have to find limit as x approaches a particular value, let us say we are trying to find limit as x approaches a, which is this point, then the limit is the value of the function at that point, which is f of a. So basically, for any continuous function, we have that limit as x approaches a for f of x is equal to value of the function a. Now this actually is a very important conclusion. We could also say that if limit of the function as x approaches a is equal to the value of function at a, that is f of a, then the function is continuous. At that point. Right, this is very important conclusion from what we have understood of finding limit of a continuous function, right? So this is huge. We can give some examples here. Some questions which you can see in the test paper could be to find limit of function as x approaches, let's say 5, and the function is pi to the power of 2. Correct? Now pi is a constant, so the value here will be pi square. So it's just a constant function, right? So constant functions are also continuous functions, correct? Or you could have example something like this, limit of let's say 2x plus 3 when x approaches 0. So for this function, if I substitute 0, I get the value 3, right? So this is equals to 3. So just substitute the value and calculate. That's what you learned, right? So these are two examples. One you could also find from the graph itself. You can read the value as such, right? So what we conclude here is that if the limit of the function at a point A is same as the value of the function, then one important conclusion we have got is that the function is continuous. So that's like going back, right? Corollary from the same thing. So I hope this concept is also clear. So let's move on and take some examples now. Now let us see how to find limits from a graph. So I'll just sketch a graph here and then we'll find limits at different points. So let's have combination of few functions in this graph. Let's say this is a whole and it's going right like this. And this point will just give some value. Let's say it is 10. And then we have another function which is kind of like this. So let's say this point is y value is 4 and the x value here is 6. Now we will include this point, and at 6 we'll give it a value which is, let us say, 16. Okay, so I'm just trying to create a function here and we'll try to find limit at different points. Okay, now for this particular function, let's say this point is minus 2 and here we have a value which is, let us say, minus 10. Okay, so in between, let's take a point somewhere here whose value is, let's say, 3 and this value is, let's say, minus 5. Okay, now based on this graph you have to answer these questions. What is the limit of the function as x approaches? Let's call this function f of x, right? So as x approaches 3, we'll find the limit of this function as x approaches 6. We'll find the limit of this function as x approaches minus 2. So let's try to figure these out. You can actually pause the video and answer this question. Now as x approaches 3, from both the sides we approach a value of minus 5 and therefore this limit is minus 5. As x approaches 6, then what we see here is that limit when x approaches 6 from the left side for the particular function is not equal to the limit as x approaches 6 from the right side, right? So it is 4 and 10 respectively. And therefore, we say for the second case, it does not exist. So the answer is does not exist. Since both these limits from left and right sides are not same. Now what is the limit of the function at minus 2? It is also at the boundary, right? So here also we'll say it does not exist. Can you tell me the reason? The reason is that the limit when x approaches minus 2 from negative side of this particular function does not exist. That is why. So both side limits cannot be same. That's the whole concept, right? Now here, few important things you will see. So let's highlight those important things, and that is, what is the value of function at 3? So value of the function at 3 is equal to -5, and it is also equal to limit as x approaches 3 for the function. So what do you note from here? So this particular thing implies that the function is continuous. At x equals to 3. Very important conclusion. If the limit is same as the value of the function, then the function is continuous. Correct? Now, what is the value of the function at 6? At 6, the value of the function is 16. Right? Do you see that? And it is not equal to limit of function as x approaches 6. And that implies that the function is not continuous. You agree with me, right? Now in this particular case, since limit does not exist, there's one more thing which we can conclude, and that is, let me write it in a different ink. So what we see here is two things, that these two limits, when you approach from the left side and when you approach from the right side, are different. So from the left side, it is 4. And from the right side, it is 10. So the limits exist but not same, right? So what you notice here is the limits exist from either side. But are not equal. That means what? That means we are looking into jump discontinuity. Now these are few very important conclusions, right? So you could figure out whether you have a jump discontinuity, whether the function is not continuous or whether it is continuous, from the knowledge of finding limits and the value of the function at a given point. So I hope this concept is absolutely clear. It's very important to understand from examination point of view. Okay. Now let's understand how to find limits when we are given a piecewise function. F of x is equal to x plus 4 when x is less than 0, x squared minus 2 when x is between 0 and 2, and is the constant value 2 when x is greater than or equal to 2. So let's try to sketch this function, and then we'll find some limits. Okay, so what we note here is that this is a linear function for less than 0. So we need 2 points for this. So let's see how to sketch this kind of a function. So when x is less than 0, then it is a line, right? So, and it's not equal to 0. So if I write 0 here, then I get a point which is at 4, right? So at 4, I get this point. So this point is a hole which is at 4. To draw the line, I have to take some other point also. If I take minus 4, then I get 0 for this function. So joining that, I get a line. So this is how I could draw this function where this point here is minus 4. Is that clear? So we took 2 points here, which is a hole 0 and 4, and the other one which we took was at minus 4 the function is 0, to draw this straight line. Now we'll talk about the parabola, the second function, where x is between 0 and 2, both are included. Both are included, right? So it's very important to understand this part. Okay. Now, if both are included, let's just substitute the value. So if I write x as 0, I get minus 2. So at 0, I get minus 2. Okay. Now we know this is a parabola. We just moved 2 units down and then. So it's kind of like this. Is it okay? We know the shape of the parabola. Fine. If I take x as 1, then the value is minus 1. And if I take x as 2, I get 4 minus 2, which is 2, right? So keeping these points, what we could do is, we could start with minus 2 here, so that is minus 2. And that's the bare minimum, and the graph actually moves to, at 2 we have 2, right? So let's say this is 2 for us, and the value 2. So we'll just move like this and join these 2 points, like a parabola. Okay. Shape is important. The third part is a constant function, which is from 2 to infinity. Okay. Now 2 to infinity is a constant function for us, whose value is 2. Now it includes the point 2, right? So basically at 2 it is 2. And even if I take a value 4, it is still 2, right? So it's a constant function which includes this point, and it's like a horizontal line. This is 2 for us. Correct. So first part, of course, is to sketch the function, to find the limits, right? So I haven't even seen what the question is. Think like this. Now we will write down some question. So we say limit as x approaches what for the particular function. So let us say we are approaching 0. Now you can see that you could approach 0 from left and right side. So I can write minus here. That means approaching 0 from the left side. Is it okay? Then let's find limit as x approaches 0 from the right side for the function. We can compare these two limits. Since there is a discontinuity, they will never match. You got the idea, right? So we can also now find limit when x approaches. This point here is at 2, right? At 2 for the particular function. Now in case of 2, whether you approach from left side or the right side, it is the same value. Okay, let me write separately. So from the left side, we put this minus on the top. And then we can write limit when x approaches 2 from the right hand side. Okay, I think you got all these answers. Let's place our answers and check the result. So when you are approaching 0 from left side, this means from left side, means this side. You are on that part of the graph and you approach the value 4. You get this? So when you approach 0 from the left side, you hit the straight line, and what you land is at 4. When you're arbitrarily close to 4, when you're sufficiently approaching 0 from the left side, that's how we'll see it, it is 4. And when you approach from the right side, you hit this parabola and reach minus 2. Now definitely these two are not equal, right? So let me show that here. These two limits are not equal, and that means what? That means jump discontinuity. So we are reinforcing our learnings, okay? Now here, in the second case, when you approach 2 from left side, you're approaching positive 2 value, and from the right side also, it's a constant function, you approach positive 2. And what you note here is that both of them are equal. So the function is continuous at x equals to 2. Function could be discontinuous, as you have seen here, but at 2 it is continuous. So I hope you are getting the point. Correct? Now, for you, the question could be find limit when x approaches 0 for the particular function. Write down this answer, and also limit as x approaches minus 4 for the particular function, right? So you could write down these limits. And how about limit when x approaches infinity for the function? Okay. So these are the three questions for you to solve. You may write down their answers. I can check them for you. So now let's move on and understand why limits may or may not exist. Now let's see why limits may or may not exist. Okay, so let's take few functions here. Let's say limit when x approaches a value 1. Okay, so let me write the function as, I'll write x minus 1 in the denominator. That means if I substitute 1, it is not defined there. However, in the numerator, I'm writing x squared minus 1. Now the limit may exist. You need to find this limit. Is it okay? So that's one of your questions. Second is limit when x approaches 0, and I'll take the function 1 over x squared. You have to find this answer, whether this limit exists or this limit does not exist. Let's take another example, which is limit as x approaches, let's say 2, and the function is absolute value of x minus 2 divided by x minus 2. Right? So here is another example. And then, final question for you is limit when x approaches 0 and the function is square root of x. Okay, so I think these are good examples to explain the point which I am going to make here. And this is going to help many of you for your test. Now the first one is, you could actually rewrite this as limit x approaches 1. Factor this out, we get x plus 1 times x minus 1 divided by x minus 1. And now you could cancel x minus 1 and x minus 1. Of course, x is not equal to 1. But you can find limit, you can approach the value, right? So then you get limit x approaches 1 for x plus 1, substituting 1, we get plus 2 as our answer. Perfect. So we find that the limit exists in spite of the fact that the function is not defined at a given point. Correct? If I have to sketch this graph, let me just make a small sketch here. How will it look like? Okay. So we finally got a straight line, x plus 1. So that means something like this, right? But it is not defined at x equals to 1. So let's say, let me just sketch a line here first. Okay, so so this point is 1 for me, but at 1 we have a hole. Do you get the idea? So, and the value, y value is 2 as x approaches 1. So it is a straight line with a difference, and that is it has a hole. So here again, x is not equal to minus 1 is a very important restriction which you should put when you're finding this limit. So limit may exist even if the function does not exist at that point. I mean, you have a hole, right? Still the limit exists. Now let's look into the second question. Now to explain this, it's better for me to sketch it. So let me use another ink to sketch 1 over x squared function. It is always positive and it will be kind of like this. So what do you notice? As you approach 0 from both the sides, you approach infinitely large value. Now, so we write this as infinity. Now, does that mean that the limit exists? That is a big question. Sometimes in multiple choice questions, you get it. We write infinity, but we are not saying it exists. Do you understand? We are saying that the value approaches arbitrarily large value. But remember, still the answer is, it does not exist. As infinity is not a real number. So this is very important to understand. We do write infinity. So it's a convenient way of expressing it is important. So we write infinity just to signify that both are approaching the same value. Do you understand? Both are going positively large value. So it means from both sides we are approaching positively large value, which is actually not defined. So we write it as infinity. Is that clear to you? So it's a huge concept. We do write infinity, but the limit does not exist. It helps us to sketch the graph and get meaningful information. So at times, if the function is approaching same side, we'll say it exists. We'll say it does not exist, but the value is infinity. Is that okay? Now let's take up the next two examples. Let me sketch a graph for absolute function. Let me make a separate one here. So at x equals to 2, if I substitute the value, I get 0 in the denominator. So what you really notice here is that this is indeterminate, right? 0 over 0. Now, in this particular case, what we have is that it's not defined at 0, right? So if I write, so this function basically is a piecewise function, as you know, right? So it is +1 for the values which are on this side. Let me sketch it in different ink. Okay. So on this side it is +1. But if the value is less than 2, let's say if I substitute here 0, I get -1, correct? So what I get here is -1. So I get a value here which is -1. So what you notice here is that at 2, the limit does not exist, since from both the sides you're approaching a different value. So it does not exist. And again, it's a jump discontinuity. Now let's take the last one, which is square root of x. Now the question for you is, what is the limit when x approaches 0 for square root x? So let me sketch this function here, square root x. So let's say we'll do this graph for square root x. You want to approach 0. Can you approach from the left side? No. So it also does not exist. You get the idea, right? You could take some other functions also where it may not exist. For example, we can have limit as x approaches 0 for 1 over x. This also does not exist. So I'm taking this example since it's a different kind of a condition. So when it is 1 over x, the graph will be kind of like this. Okay. So from all these conditions, what do you conclude? Why the limits may exist or why don't they exist? That's the question for you. So for the first part, may exist. They may exist if the limit from left side is equal to limit from right side. Then they may exist, just as we have a case here. The limit exists in spite of the point not being a part of domain, because the concept is approaching, not being there. And from both the sides, you approach the same value. So if those values are same, let's say L, then the limit exists. Perfect. And the limit may not exist if they are not same. Simple as that. So if the limit when x approaches a from the left side for any function is not equal to limit when x approaches a from the right side, it does not exist. Very simple. So that is the basic concept. Now looking at the graph, if the function is approaching infinity, then the limit does not exist, right? So one thing else which is important to see, if f of x is approaching positive or negative infinity, right? In that case, limit does not exist. We're talking about as x approaches the point A, right? From positive side or from negative side. So those are the conditions where the limit will not exist. So I hope this concept is clear to you, right? With these examples, which are very popular examples. And now we'll actually get into finding limits for different types of functions. Now in this particular part of the video, we will see how to find limits as x approaches infinity. So I have two examples here. X approaches positive infinity. In the second case, we are talking about x approaches negative infinity. You can always pause the video, answer this question, and then look into my suggestions. Now a few important concepts before I get into this. As we have discussed many times, you should know what is square root of x square. That is going to help us to solve the second question. Now the technique for finding limits for rational functions especially is, well, from the equation you could get the answer. The answer here is 2 over 5. Very easy. So from a multiple choice question, you could easily find that is the answer. Now let's see the reason why. So the reason is kind of like this. We are trying to find the limit as x approaches infinitely large value. Factor out this x square, right? So whatever maximum you can from a particular equation, I say expression. So in this particular case, I could factor out x square. So what I get here is 2 plus 3 over x plus 4 over x square, correct? And the denominator for me will be, I can again factor out x square here. I get 5 plus 6 over x plus 7 over x square. Perfect. Now, it is important to note that 1 over x or 1 over x square approaches 0 as x approaches infinity, right? So that is very important to understand. And that really means that both these terms in the numerator and also in denominator approach 0 when x is approaching infinity. Is that part clear? And this is huge, right? So we could write this as limit x approaches infinity. And now, before we go further, we'll also cancel these x squares. What are you left with? We are left with just 2 over 5. Do you see that? 2 over 5, which is a constant, and therefore the answer is 2 over 5, which basically is the ratio of leading coefficients. If same degree for numerator and denominator. So whenever the degrees are same, you get this. And we have also learned a concept of horizontal asymptotes, right? So at time, it is a fixed value. So by definition, we understand this is also horizontal asymptote. So sometimes in the equation, you may have to find the equation of horizontal asymptote, which will be y equals to 2 over 5. Does it make sense to you? Correct? So that's how it should be solved. Now let's take the next example, which involves square root in the denominator this time. Now we'll follow the same technique. Okay, we'll follow the same technique and see how it is different. We could rewrite this as limit x approaches minus infinity, so we'll take factor out x in this case. Minus infinity it is, okay. So we have 1 over x plus 2. We have factored x from the numerator. In the denominator, we'll do it in 2 stages. So first stage, I'll factor out x squared. You're left with 9 plus 25 over x squared, correct? Now, 25 over x squared is very small. Okay, so we could write this as limit x approaches minus infinity. Numerator is x, 1 over x plus 2, right? And the denominator, what is square root of x squared? The square root of x squared is absolute value of x. It is not just x. So if you write x, you'll get a wrong answer here since we are approaching negative infinity. So it is absolute value of x, and within square root, the second quantity term is 0, 25 over x squared. As x approaches large value, you are left with 9. This part is 0. It is approaching 0, right? So I'm purposely writing, no need to write, since x is approaching minus infinity. Is it okay? Now, we are only approaching, we are not finding exact value. Now, what is absolute x when x approaches negative infinity? If x approaches negative infinity, then absolute x is equals to minus x, right? And therefore, we could write this as limit x approaches minus infinity for x times 2, because this is also approaching 0. So I'm writing 2x now. Since the term, this term and this term are approaching 0, we are left with 2 in the numerator, okay, divided by minus 3x. Square root of 9 is 3, minus is because of absolute value approaching minus infinity. You get the idea. So it is minus 2 over 3 as our answer. The xx can now be cancelled. You get it. So the answer for this is minus 2 over 3. So this function is going to have an horizontal asymptote. When x approaches negative infinity, the value is minus 2 over 3. Okay, so that's how you will do it. Not positive 2 over 3. Remember that part. So the knowledge of square root of x squared helps, and understanding absolute functions is very important and critical for calculus. So let's move on and now do questions related to indeterminates. We'll solve limits of indeterminate quotients. We have 2 examples here. The first one is limit x approaches 1 for x cubed minus 1 over x minus 1. So if I substitute 1 here, I get 1 minus 1 over 1 minus 1, which is 0 over 0, right? So this is we call indeterminate. Quotients. Quotients, since you are dividing something by the other. Now, whenever that is the case, which is also the case in the second example, you're approaching 4. So square root of 4 minus 2 over 4 minus 4 is also 0 over 0. So if that is the condition, you could apply some techniques. Factoring is a very effective way. We'll learn substitution, rationalization, L'Hopital's rule, and many other techniques in this video. So what we should do now here is rewrite the function in factored form. That is best for this kind of question. Expand x cubed minus 1. What we get here is x minus 1 times x squared plus x plus 1. Correct? That is the expansion for a cubed minus b cubed. Divide by x minus 1. Now this x minus 1 cancels. So we can write this as limit x approaches 1 for x squared plus x plus 1. Applying the laws of limits, which is you could add their limits individually. We just substitute the value. We get 1 plus 1 plus 1, which is 3. Clear? So that is how it should be done. Now next example, again, we could do it by rationalization, but we'll do it by factoring here. Now you could write this as limit x approaches 4. So the numerator is square root 2. The numerator is square root x minus 2. Now we could think about denominator as square root x square minus 2 square, right? When x is approaching 4, we're talking, right? So we're taking this as positive x. So this could be written as limit x approaches 4, and we could factor this. So we get square root of x minus 2 divided by square root of x minus 2 times square root of x plus 2. So now we have a common factor in numerator and denominator which could be cancelled. And once they are cancelled, you substitute 4 here. So what you get here is limit x approaches 4 for 1 over square root of x plus 2. And substituting 4, we get 1 over square root of 4 plus 2, which is 1 over 2 plus 2, which is 1 over 4. So we get this limit as 1 over 4. And the limit for the first one is 3. Correct? So that is how we could do it. I hope the steps are simple and useful. I've taken up 2 examples where we are going to apply substitution method to find limits. Limit when x approaches 1 for x to the power of 1 over 6 minus 1 divided by x to the power 1 over 3 minus 1. If I substitute 1 here, I get 1 minus 1 over 1 minus 1, which is 0 over 0. So it is again indeterminate form. So that means we have a common factor. So last time we learned how to get rid of that common factor. Now we will learn how to use substitution. Now here also, if I substitute 0 in x plus 8 to the power of 1 over 3 minus 2 over x, we get 0 over 0. So that is also indeterminate form. So let's see how to use substitution now to solve such a question. So let's substitute x to the power of 1 over 3 as some value as, let's say, p. In that case, what is going to be x to the power of 1 over 6? It is going to be p square, correct? So what we get here is, we could rewrite this question as limit x approaches what? Now we have to find that value also. So when you substitute x cube root of x as p, you have to find if x approaches 1, p approaches what? So p approaches cube root of 1, which is also 1. So we could rewrite this question as limit p approaches 1, and in the numerator we have p square minus 1. In the denominator we have p minus 1. You get my idea. Correct? So now we could rewrite this as limit p approaches 1 and factor this. So we got p minus 1 times p plus 1 divided by p minus 1. Now p minus 1 and p minus 1 cancels, and substituting p equals to 1, we get answer as 2. So this limit is equal to 2. You get the idea, right? So that's how you do it. So I'd like you to pause the video and try out this question now. So what substitution should I make? Now here we'll substitute x plus 8 to the power of 1 over 3 as, let's say, p. In that case, what is x equals to? Well, rearrange. It becomes p cubed. So x is equal to p cubed minus 8. Right? So if I write x plus 8 cube root as p, then p cube, when you cube it, minus 8 is going to be x. One part. Second is, as x approaches 0, p approaches what value? P approaches 0 plus 8 cube root, which is cube root of 8, which is 2. So now we'll rewrite this question with these 2 substitutions. Limit is p approaching 2. Here we have p minus 2 in the numerator. The denominator is p cube minus 8. Got it? So now we could write this as limit p approaches 2. Numerator is p minus 2. Factor the denominator. 8 is 2 cube. So we get p minus 2 times p square plus their product, which is 2p, plus 2 square, which is 4. Right? Now you could cancel the common factors. That's the whole idea. We got 0 over 0 simply because there was a common factor. And then you can substitute 2 here. So we get 1 over 2 square plus 2 times 2 plus 4. So which is 1 over 12. So the answer here is 1 over 12. You get it. So that is how substitution can effectively help us to solve limits. So let's move on and now take up examples with rationalization. Now in these two examples, we have square root, and if I substitute 0, what I get? I get square root of 1 minus 1 over 0. 1 minus 1 is 0. I again get 0 over 0. So it's an indeterminate form. So in this particular case, we could use the technique of rationalization. Let us see how to apply rationalization. Let's rewrite this as limit x approaches 0. We have square root of x plus 1 minus 1 over x. We'll multiply and divide by the conjugate of the numerator, which is square root of x plus 1 over square root of x plus 1 plus 1. Now, when you expand, in the numerator you get difference of squares, correct? So we get x plus 1 minus 1 square, which is 1, divided by x times all this, which is square root of x plus 1 plus 1. Now, numerator is only x, correct? So we could write this as limit x approaches 0 of x over x times square root of x plus 1 plus 1. So now we can cancel the common factor x, which was giving us 0 over 0. And it gets simplified to 1 over square root of x plus 1 plus 1. Now substituting 0, we get 1 over 1 plus 1, which is half. So this limit is indeed half. Correct? Now let's look into the second example where it's kind of different. I'm taking limit when x approaches infinity. Now how do we do these types of questions, right? Now if I write infinity here, we get infinity minus infinity. That is also a form of indeterminate, right? So this is also indeterminate. Difference, not quotient, but difference. Now in such cases, you could rationalize. So we'll again rationalize like we did earlier to solve this. So we'll limit x approaches infinity. We have square root of x plus 1 minus square root of x. So you have to multiply and divide by the conjugate, which is square root of x plus 1 plus square root of x. Clear? So that gives you limit x approaches infinity. You got difference of squares here, which is x plus 1 minus x divided by all this, which is square root of x plus 1 plus square root of x. Now, in the numerator, x cancels. So we are left with what? So in this particular case, we are left with just 1, right? So 1 over square root of x plus 1 plus square root of x. Now, if I substitute infinity here, then we get something over, like kind of like this, 1 over infinity, right? Which is 0. So the limit exists, and at infinity, we are approaching 0. You get the idea, right? So it's in the denominator. Perfect. So 1 over infinitely large value is 0. So that is the answer. So that is how you solve. So I hope you understand and appreciate this example. It's very important from test point of view. Now, let's take up trigonometric functions. Now we will take a few examples which are AP calculus level. So we'll begin with trigonometric functions. How do we find limit of trigonometric functions? Well, you have to remember the basic formulas to solve these questions. So we have 1 minus cos 2x over x. We need to find limit when x approaches 0. Now if I substitute 0 here, what do I get? I get 1 minus cos of 0 over 0, which is 1 minus 1 over 0, which is of the form 0 over 0. It is the indeterminate quotient form, so we need a very special treatment to solve such questions. Now let's see how to solve it. You also know that cos 2x is equal to 1 minus 2 sine square x. If you rearrange this formula, you get 2 sine square x equals to 1 minus cos 2x. So the numerator can really be written as 2 sine square x. So we'll rewrite this question, which is to find limit as x approaches 0 for 1 minus cos 2x over x. We can actually write this as limit x approaches 0. The numerator is 2 sine square x over x. Now, you know what is limit of sine x over x. So it is a good idea to rewrite this as product of sine x and 2 sine x. So we write this as, when x approaches 0, we go write this as sine x over x times 2 sine x. Right, so we go write this as this. Now, it really helps us to find the limit, since you know that limit of sine x over x when x approaches 0 is 1. So it could be written as limit of sine x over x times 2 is a constant. I could write it here. Let me write limit x approaches 0 for sine x. Now the first term here, limit for sine x over x is 1. So what we get here is 2 times 1. However, limit for sine x when x approaches 0 is 0. So when you multiply this, what you really get is just 0. So that becomes the limit of the function as x approaches 0. So I hope that concept is clear. So we use a couple of things here. One, the knowledge that limit x approaches 0 for sine x over x is equal to 1, and the application of double angle formula. So I hope that is clear. Now to really get all the questions based on trigonometric functions, you have to recall all the formulas you have learned for compound angles. Now let's move on and take some examples based on logarithmic functions. Now we have two examples here where we'll try to see how to apply L'Hopital's rule to find the limits. Limit when x approaches 9 for square root of x cubed minus 27 divided by x minus 9. Now in this particular case, if I substitute 9 here, then I get 9 cubed square root minus 27 over 9 minus 9. Now that is 0 over 0, right? So that's an indeterminate form, and here we can apply the L'Hopital's rule. In the second example, we have limit when x approaches infinity for ln x over cube root of x. Now if I substitute infinity here, then we get what? We get ln infinity over cube root of infinity, right? So this is of the form infinity over infinity. Now both of them are indeterminate quotient forms, right? So we have So in this case, we can apply the L'Hopital's rule. The rule basically is to find the derivatives of numerators and denominators. So the limit remains same when we find the derivatives of numerator and denominator. So we could rewrite this function as limit x approaches 9, derivative of x cube, which is the power, let me write down, d dx of x cube, 3 over 2, square root of x cube, minus 27, divided by the derivative of x minus 9. Correct? Now, the derivative of this is, let's rewrite, 3 over 2, that constant is 0, so we get 3 over 2 in the numerator, times x to the power of 3 over 2 minus 1, right? So that means square root. Over derivative of x is 1. That's what we get. Now if I substitute 9 for x, what do I get? I get 3 over 2, 9 square root, right? Which is 3. So we get 9 over 2 as our answer, 4.5. So the answer here is 9 over 2. So that is how you could actually find derivative of such function very easily. Perfect. Now we have another example here. We need to find limit when x approaches infinity for ln x divided by cube root of x. So again, applying the L'Hopital's rule, we can say that this limit is equal to limit when x approaches infinity for the function derivative in the numerator and derivative in the denominator, right? Let me write x to the power of 1 over 3. Now the derivative of this function, ln x, is 1 over x. So let me write here 1 over x for the numerator, limit x approaches infinity divided by cube root 1 over 3 x to the power of this minus 1, which is minus 2 over 3. Now that gives you limit x approaches infinity. So we could write this as 3 over, that x comes in the denominator, and this we could write in the numerator as minus, so it is negative 2 over 3, correct? So you could write like this. Now, basically it is, or you could say x to the power of minus 1, which is equal to limit x approaches infinity for 3 times x to the power of 2 over 3 minus 1 is x to the power of minus 1 over 3. We could have written like this. Okay. So that means it comes in the denominator. Basically, higher power is in the denominator. So I'm just rearranging. X approaches infinity for 3 over x to the power of 1 over 3. Okay, so I could have added them here. Since x is infinitely large, this function approaches 0. So the limit of this function is 0. Does make sense. So that is how we could actually solve this particular question. Now let's take another example where we will see how to apply the squeeze theorem. Now here is the last example. I hope you enjoyed this journey of quick review on limits. We took a variety of questions. Squeeze theorem. Now let's find the limit using squeeze theorem. Limit x approaches 0 for x squared sine 1 over x. Now as you know, the value of sine theta is always between plus and minus 1, correct? Somewhere in between. Now in this particular case, we could use this property to find the limit by squeezing the value as x approaches 0. That's the whole idea, right? So let's see how to do it. So we begin with this fact. In this case, we have sine of 1 over x, and that value has to be between negative 1 and positive 1. Now if I multiply by x squared, which is always positive, right? So we could do that since we know x squared is greater than 0. greater than or equal to. So we could do that. So in that case, it will be multiplying by x square. We get minus x square less than equal to x square times sine of 1 over x should be less than equals to x square. So we multiplied the whole expression, inequality, with x square. Now, if you look into this, what happens when x approaches 0? Now, if x approaches 0, both these terms will approach 0. Correct? So that means the value of this function gets squeezed between these two zeros. So what should it be? Nothing but 0. You get the idea, right? So from here, we get that x squared times sine 1 over x is between zeros, and what is there between them is only 0. Therefore, this limiting value is 0. You get the whole idea, right? So that is how squeeze theorem can be applied, and very difficult questions could be solved very easily using this theorem concept. So I hope that's absolutely clear. Feel free to write your comments and share your views. If you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.